You'll look at a drill bit and you probably think, yeah, I know what that is. It's just a simple, pointy spiral thing, right? Well, what if I told you that this everyday tool is actually a masterpiece of high-tech engineering, that every single curve and angle is making a series of tiny, brilliant decisions? In this explainer, we're going to dissect the anatomy of a drill to see what really makes it tick. It really all comes down to this one simple question. What does it actually take to make a perfect hole? I'm not talking about just a rough opening. I mean a hole that is perfectly round, exactly the right size, and precisely where you need it to be. Well, the answer isn't about brute force. It's all about intelligence, specifically the intelligence that's literally baked into the tool's geometry. See, the real secret to a perfect hole is this cascade of tiny, brilliant decisions made by the shape of the metal itself, long before you even turn the machine on. So let's start right where all the action happens, the tip. This is the business end, right? The part of the drill where that critical first contact is made. And believe me, everything that follows depends entirely on what happens right here. It's kind of crazy how much rides on this one single feature, the point angle. This isn't just about being sharp. This angle dictates the entire physics of the cut. It controls all the forces at play and basically decides what kind of material the drill is even built to handle. And this just shows you how specific that engineering gets. A 118-degree angle? That's your go-to for softer, gummier materials. But jump up to 135 degrees, and now you've got the perfect geometry for something tougher, like aluminum and stainless steel. For the really hard steels, you need an even broader 140-degree angle. It is a perfect match of geometry to the material. And here's a perfect example of geometry solving a super common problem. Have you ever seen a drill kind of skitter across a metal surface before it digs in? Well, that's called walking. To stop that, machinists use a spot drill with a really wide 150-degree angle. It just creates a perfect little cone for the main drill to follow. It's like a guide that ensures absolute accuracy right from the get-go. Now, right at the very center of the tip, you've got these two key players working together. First, the chisel edge. It doesn't actually cut. Its job is to push or extrude the material out from the center. This perfectly centers the tool and feeds material right into the super sharp cutting edges, which then slice it away into chips. So one part stabilizes, the other slice. It's a perfect team. Okay, so let's move up from the tip to the body of the drill. I mean, once a chip is created, it's got to go somewhere, right? The body is designed to be this incredible material superhighway, built just to get those waste chips out of the hole as fast and as efficiently as possible. Now, the most recognizable part of any drill has got to be its flutes, but they are definitely not just for looks. The best way to think of them is like an elevator system. As that drill spins, these deep grooves catch the chips being made at the tip and just lift them up and out of the hole. This prevents a jam that could totally wreck both the tool and the part. Okay, so if the flutes are the elevator, then the helix angle, that's the design of the elevator system. It's the angle of that spiral, and it is precisely tuned to control how aggressively those chips get pulled out of the hole. And just like with the point angle, the right helix angle depends completely on the material you're cutting. So here's the deal. Different materials break in totally different ways. You've got brittle stuff, like cast iron, that creates these little short chips. For those, a low helix angle works great. But then you have materials like aluminum that create long, stringy chips. For that, you need a high helix angle, basically a faster elevator to yank that debris out before it gets all tangled up. The web, that's the solid core of the drill, it's its backbone. A thicker web means you've got a stronger, more rigid tool that can handle a lot more twisting force. But, and there's always a but, here's the trade-off. A thicker web also means smaller flutes, which gives the chips less room to escape. So engineers are always in this balancing act, trying to find the perfect sweet spot between strength and chip evacuation. All right, we've made the cut and we've cleared the chips. Now let's get into the really subtle features, the ones that make sure the hole isn't just empty, but is perfectly finished. I'm talking smooth, round, and on size, right down to the micron. If you look really close at the corner where the cutting edge meets the outside of the drill, you might see this tiny angled surface. That's a corner chamfer. And this little detail, it is an absolute workhorse. It strengthens the most vulnerable part of the cutting edge, which makes the tool last way longer, and it helps create a cleaner exit, reducing all those messy burrs. The drill margin is this narrow raised strip that runs right along the edge of the flute. And its job is incredibly important. Think of it like guide rails on a train track. As the drill cuts deeper, the margins make contact with the inside wall of the hole, stabilizing the tool and making sure it drills perfectly straight instead of wobbling all over the place. And you guessed it, we're back to another one of those classic engineering trade-offs. Wider margins, they give you more stability, which means a more accurate hole, but they also create more friction and heat. Narrower margins cut down on that friction, which is great for the tool's life, but they offer less guidance. The choice really comes down to what's more important for a specific job, absolute precision or making the tool last longer. So what happens when things get really tricky? Like if you have to drill through an existing hole or exit on an angled surface? Well, a single margin just isn't enough to keep the drill from bending. That's why some drills have 2 or even 3 margins. Those extra points of contact give it the stability it needs to stay perfectly straight, even in the toughest cuts. Okay, now for a huge rule of thumb in next-gen manufacturing. Anytime you have to drill a hole that is deeper than 4 times the drill's own diameter, what machinists call 4XD, a whole new factor becomes absolutely essential, and that is coolant. And the absolute best way to deliver that coolant is with coolant through drills. These things have tiny channels running right through the center of the tool, pumping high-pressure fluid directly to the cutting edge. This blast chips out of the way, it lubricates the cut, and it keeps everything cool. I mean, it lets you drill dramatically faster and deeper, and the results are just incredible. So, after all these tiny, almost microscopic details, let's zoom out for a second. Why does any of this matter? Well, because this level of precision, engineered into what seems like a simple tool, is truly the foundation of pretty much all modern technology. Heck, even the part you don't usually see, the shank, is critical. This is the part that gets clamped into the machine. If its diameter is off by just a fraction of a human hair, the whole drill will be misaligned. And all that brilliant geometry we've been talking about at the tip, it becomes completely useless. The entire system has to be perfect. So, what's the big takeaway here? At the end of the day, in manufacturing, geometry dictates performance. Every single feature is a carefully calculated trade-off. And it's this obsessive attention to detail that makes everything from the phone in your pocket to a jet engine possible. Understanding the tool really is the first step to mastering the craft. And this really hits the nail on the head. For a machinist, this isn't just some academic exercise. Understanding these geometries is a practical necessity. It's how you choose the right tool for the job, how you troubleshoot problems, and ultimately how you push the boundaries of what's possible. Which really leaves us with a final thought to chew on. If a common, everyday drill bit has this much hidden science and deliberate design packed into it, how many other simple objects in our daily lives are just loaded with a level of engineering we never even see? What else are we overlooking every day?